continue. Okay, so alright, so in saturated soil, okay, so if you are talking about soil that has a water table above it, okay, just above the water table, the soil will remain saturated due to capillary, but at some distance above water table, the water still unsaturated. So, okay, so like if you can see from the figure here, we have a dry unit weight above the water table, and we have a saturated unit weight below the water table. Okay, so below water table, it is always saturated soil. So you have to use unit weight of saturated soil. Okay, so let's say we are talking about effective stress at this point. If you can see my pointer here, okay, it is gamma ZW here, okay, which is unsaturated, plus gamma saturated for this layer multiply with this depth Z minus ZW. Okay, so at this point we have a combinations of two different unit weight here. Okay, sometimes it can be the same material, but then above water table it is dry, below water table it is saturated. Okay, so for above water table you need to use the unsaturated unit weight. It can be dry or bulk density, depends on the situation. Okay, but below the water table the total stress is always considered the saturated unit weight. So in this case, at this point, we have gamma ZW, okay, and then gamma saturated multiplied with Z minus ZW. Okay, so what if we have a surface charge load? Okay, for instance, the load that comes from building, comes from road, maybe tank, anything that you have that impose a load on the ground surface. Okay, so you have to consider that as well. Okay, so we have surface charge which is Q. So if you are talking about total stress at depth Z, it is surcharge Q plus with gamma Z. Okay. For water pressure, water in pores of soil is called pore water. So the pressure within that pore is called pore water pressure. Okay, at water table, okay. So at the level of water table, pore water pressure equals to 0. Okay, and the magnitude of pore pressure depends on the depth below the water table and the conditions of the seepage flow. Okay, so effective stress then, it is, as I said, it is effective stress equals to total stress minus pore water pressure. So effective stress is the load or average stress carried only by solid grains. Okay, so for instance, if you have water table at ground surface, okay, okay. So if I can draw here, okay, for the first one, okay, so okay, so for water table at ground surface, okay, let's say this is your soil, okay, and then you want to consider stress at this level, okay. So let's say here is Z, okay. If water table at ground surface, okay, let's say you have water here, water table at ground surface. So total stress is because it is below water table, so the soil below that is saturated, so you have to use saturated unit weight. So total stress become saturated multiplied with Z, and then pore water pressure is unit weight of water multiplied with Z. So effective stress is always total stress minus pore water pressure. Okay, so if you write them again, we have total stress which is here. So we have here minus with for water pressure. So you have this, then you end up having with what we call effective stress multiplied with Z. Okay, as you've learned before, effective unit weight, it is always saturated unit weight plus, minus unit weight of water. Okay, so this is also another standard equations. Okay, so if you write them, it is actually, so total stress, so for this case, total stress is gamma saturated Z. So if you're talking about effective stress, it is actually using effective, so it's effective stress multiplied with Z. Okay, right. And what if we have water table at depth ZW below ground level? Okay, so let's say we have a case like this. Okay, and let's say I would like to consider at depth Z. Okay, at this level. Okay, and let's say we have water table somewhere here. Okay, so total stress for this case, all right, so above water table it is bulk unit weight or dry unit weight. Okay, below water table it is always saturated unit weight. So from here to here, okay, you have total stress is gamma times ZW, okay, plus gamma saturated Z minus ZW. Okay, so let's say this is ZW. Okay, so that is total stress. So for water pressure, it is gamma W Z minus ZW. Okay, so for water pressure is calculated where you start to have a water. So it's actually this depth. So this depth is Z minus ZW. So that's why you have for water pressure equals to gamma W multiplied with Z minus ZW. And finally, you have your effective stress. Okay, which is total stress minus per water pressure. Then you have gamma ZW plus gamma saturated Z minus ZW minus gamma W ZW. Okay, so it is gamma ZW plus gamma saturated minus gamma W is effective unit weight. So you have gamma effective multiplied with Z minus ZW. Okay, boleh? So far, any problem? Yeah, anybody has problem here?
No, doktor.
No ke? Apa? Tak dengar?
No, doctor.
No,
Okay,
doktor.
good. Okay, so can we proceed?
Sure, doctor.
Okay. So then we have what we call effects of capillarity. So if you have silt and sands, okay, the soil above groundwater sometimes can be saturated by capillary actions. Okay, so let's say this is your ground surface. Okay, let's say here's silt or sand, and you have water table somewhere here. Sometimes the silt and sand can be saturated where the water is actually coming up to here, okay, due to effects of capillarity. So before this, what we did is we say that for this level is either dry or bulk unit weight, right? Okay, but then if you have silt and sand, there is a possibility where you have what we call effects of capillarity, where the water is coming out and saturated the soil here. Okay, and this is the depth for capillarity, also known as ZC or HC. Okay, and the pore water pressure due to capillarity is negative. Okay, so as I mentioned before, pore water pressure at the water level equals to 0. Okay, as you go deeper, you're going to have a positive value. Okay, but if it's effects of capillarity, for instance here, you will have U which is negative value due to suction. Okay, because the suction that caused the water to saturate this area. Okay, so pore pressure due to capillarity is negative value. Okay, so at ground level, U is 0 and decreases become negative as you move the capillary up the capillary zone. As it going up, you're going to have negative value. So increase because of negative pore water pressure, then you actually increase the effective stress. Okay, because total stress, effective stress is total stress minus pore water pressure, but due to capillarity, okay, so your pore water pressure is negative value, so you're going to actually increase the effective stress. Okay, and here ZC or HC is depth of the capillarity. Okay, so U here is negative ZC. Okay, boleh? Alright, and then effects of seepage. As water flows through soil, it exerts a frictional drag on soil particles, results in head loss. Okay, yang ni you dah familiar with those terms. Okay, and the frictional drag, okay, also known as seepage force in soil mechanics, and it's defined and the unit is force per unit volume. So you have kilonewton per cubic meter and denoted by JS. Okay, so if head loss over a flow distance L, okay, so delta H is JS, distance L is delta H, so your frictional drag, which is JS, equals to delta H over L multiply with unit weight of water. So as you've learned before, delta H over L is also hydraulic gradient. Okay, so you end up having JS equals to I multiply with unit weight of water. Okay, so if the seepage occurs downward, same directions as gravity, you're gonna have it's actually increase the effective stress. Okay, so gamma prime Z plus I gamma W multiply with Z. Okay, so it's actually this, alright. And if it occurs upward, where it's going opposite direction of gravity, you have to minus them. So the effective stress is effective unit weight multiply with Z minus with frictional drag multiply with Z. Okay, so that is if effects of seepage, and you have to check the flow's direction. Okay, okay, so principle of effective stress is very important in soil mechanics. Okay, as you can see here, time 0, for instance, effective stress is 60. After 8 months, after you have the building, okay, and the pore water pressure also increase, then you still have the same effective stress. And then after 12 months, okay, the total stress still the same, but then the pore water pressure getting lower because the waters move away from the soil, so effective stress is become higher. Okay, and after 20 months here, it's become even higher. Okay, because water expelled from the soil, more water expelled from the soil, so you have less pore water pressure. Okay, Okay, here are the notations for stresses. Okay, either compressive or tensile. Okay. If it's vertical, then it is sigma V. Okay, here is shear stress. Okay, and if you can see here, stress at x and y directions are horizontal stresses, also known as lateral pressure. Okay, for this one, it will be covered in soil mechanics too. Okay, so total stress equals to effective stress plus pore water pressure. Okay, so and when pore water pressure equals to overburden pressure, effective stress becomes zero. Then we have what we call here liquefactions. Okay, so basically liquefaction happens when you have a partially saturated soil and then there's a drastic impact. Okay, for instance, earthquake. Okay, so what happened is the phenomenon known as liquefactions, where the soil then become like a fluid. Okay, so and it caused, for instance, in Japan here, 1964, you can see all the building collapse. Okay, so that's all. Okay, so that's the explanations. Okay, that is assignment. But before we go there, I would like to show you a few examples. Before we finish, I have two examples to show you. Okay. Okay. So first example. Uh, okay. Here, calculate effective stress. Calculate effective stress for a soil element at depth 5 meters in a uniform deposit of soil as shown below. Okay, so for example, we have a ground level, okay, and up to 2 meters. Okay, here given to us degree of saturation is 60%, and then water content is 30%. And then below we have water content equals to 40%. So question asks to find effective stress at 5 meters. Okay, so another 3 meters here. So at this point, okay, we need to find the effective stress. Okay, all right. So and we have a water table here. Okay, so we have a area here with a degree of saturation of 60%, water content 30%, and then we have water table at 2 meters below ground surface. Okay, where below ground surface the water content is 40%. So question asks to find effective stress. So first we need to find total stress, but before we can do that, we need to calculate unit weight. How much is unit weight here? How much is saturated unit weight here? Okay, above the water table, it is just unit weight. Okay, and below groundwater table, it is saturated. So we can consider that SR equals to 1 or 100% because it is saturated. So above groundwater level, okay, so from the information given to us here, okay, SRE equals to WGS. So SR is 0.6, E and W we have 0.3. Okay, so in these questions, GS given to us as equals to 2.7. So multiply with 2.7, so you end up having E equals to 1.35. Okay, and then unit weight is GS 1 plus W over 1 plus E gamma W. Okay, so it is 2.7, 1 plus 0.3 divided by 1 plus 1.35 multiply with unit weights. Okay, multiply with unit weight of water, which is so multiply with 9.8. Okay, so then you have unit weight equals to 14.6 kilonewton per meter cube. Okay, so below groundwater level, okay, because it is saturated, so SR equals to 1, so SRE equals to WGS. So SR1 multiply with E, W is 0.4 multiply with 2.7, then you have E equals to 1.08, and then saturated unit weight, okay, it is GS plus E over 1 plus E multiply with gamma W. So 2.7 plus 1.08 divided by 1 plus 1.08 multiplied with 9.8. Then saturated unit weight equals to 17.8 kilonewton per meter cube. Okay, so now we have the informations needed for our calculations. We have above water level is 14.6 and below water level is 17.8. Okay, then using those informations, okay, then we can calculate our total stress. So total stress, okay, so for the first 2 meters, unit weight multiply with 2 meters plus saturated unit weight multiply with 3 meters. Okay, we are talking about stress at 5 meters. So it was 14.6 multiply with 2 plus saturated just now is 17.8 multiplied with 3 meters, then we have 82.6 kPa. Okay, and then total pore water pressure, okay, it is gamma W multiplied with 3 meters, okay, at depth 2 meters, so ZW is 3 meters, so 9.8 times 3, then you have 29.4 kPa. So you're having effective stress equals to total stress minus U. Then it is 82.6 minus 29.4. Then you have what we call the answer is 52.3 kPa. Okay. Alternatively, okay, effective unit weight is total. Effective stress is total over. Total stress minus pore water pressure. Okay, as I said, above groundwater level, normally we use the dry or bulk unit weight. Okay, and below water level, it is always effective for effective stress. So we have gamma times 2 meters plus effective times 3. Okay, so it is actually 14.6 times 2, where effective is saturated minus W, so 17.8 minus 9.8 multiplied with 3. So you still have 53.2 kPa. Okay? So far boleh faham
Boleh.
Right. Okay. So that is if you have a multi-layered soil. Okay. Let's do another example. Okay. For seepage. Right. Example 2. Let's say you have a ground level, and then you have your piezometers. Piezometers is used to measure the water level. Okay, let's say you have your piezometers here, and the distance between these two is 2 meters. Okay, and given here, the saturated unit weight below here is 18.5 kilonewton per meter cube. Okay, so questions ask for water is seeping downward through a soil layer. Okay, so water is seeping downward through. Okay, so the keywords is seeping downward. Okay, we have two piezometers A and B, which is 2 meters apart. Okay, and the head loss given to us as 0.2 meters. Okay, so question asks to calculate resultant vertical effective stress for a soil element at depth of 6 meters. Okay, so this is seeping downward. Okay, so we have delta H given to us as 0.2 meters, and then we have the piezometers which is apart from each other by 2 meters. So L, we are talking about 2 meters. So from this we can calculate hydraulic gradient, which is delta H over L. So 0.2 divided by 2, so we have I equals to 0.1. Okay, so to determine effective stress at 6 meters, okay, so it is saturated minus gamma W, the effective stress, effective unit weight multiplied with Z, plus, because it's seeping downwards, so plus I gamma W Z. Okay, So Z now, the questions of ask for Z equals to 6 meters. So somewhere here 6 meters. Okay. So saturated unit weight given to us 18.5 minus unit of water 9.8, all multiplied by 6 plus I 0.1, gamma W 9.8, Z again 6 meters. So you end up having effective stress equals to 58.1 kPa. Okay, so if it's seeping upward, you have to change here to become minus. Okay.
Doktor. Doktor.
Yeah, I'm listening.
Dia ada keyword lain ke selain shipping upward and downwards tu?
Apa dia? Ada apa?
Keyword lain ke dia memang bagi tahu macam tu je?
Macam tu je. Sebab this one effects of seepage.
Ah,
Yang ni contoh, this second example is example for effects of seepage.
okay.
The first example is for multi-layered soil. This one is effects of groundwater level, effects of water table. Okay. So you might have questions where we have different types of soil below the ground surface. Okay, and there's also a possibility of having a surcharge as well. So for instance, you've been given a surcharge Q is 100 kPa, then you have to add up the surcharge into the calculations. Okay, so tapi example ni tak adalah. So I'll erase this one. Nanti kan yang tengok ni confuse pula kan. Tak kira tapi ada pula kat sini. Alright. Okay, so the assignments, okay, very easy actually, but you have to try and submit. Okay, here. To be submitted by next week in Putra Blast. Okay, senang je. Ini you buat paling lama pun 20 minit pun. Macam tu lah. Alright. So a borehole, okay, so when we do site investigations, we also have what we call bore lock, okay, where you excavate a boring, you do a boring and then you do some tests and you bring some of the material, you take the sample and bring to the lab, and then you have all these informations. Okay, so a borehole at reveals a soil profile like this. Okay, plot the distributions of total and effective stresses with depth. So I would like to see the distributions of total stress and also distributions of effective stress over depth. Okay, when I say distributions means I would like to know how much stress at all layers. Okay, so here we are talking about at 2 meters, 3 meters, 5.4 meters and 20.6. So how much is total stress at this point? How much total stress at this point? How much total stress at this point? How much total stress at this point? And then I also like to see distributions of effective stress again at this point, at this point, this point, and this point. So to for you to come to the effective stress, you will need another distributions, which is distributions of pore water pressure. Okay, because effective stress equals to total stress minus pore water pressure. So here is total stress, here is effective stress, here is pore water pressure. Okay, and if you look here, we have fine sands. Okay, from 0 to 2 meters is very fine wet sand with silts, where information is given to you here. water content is 5%, degree of saturation is 40%. So you have to do like we did in first example just now, you have to calculate all the unit weight. Okay, and then from 2 to 3 meters, it is fine sand saturated by capillary action. Okay, that fine sand is actually the same with fine sand below here. Okay, where water content is 12%. So from 3 to 5.4 meters, it is fine sand with 12%. Actually, from 2 to 5.5, 2 to 5.5, from 2 to 5.4 meters, they are all fine sand. It's just that you have water table here. Okay, so below the water table, they are all saturated. Okay, but then in this case, we also have fine sand saturated by capillary actions. So from here to here, we have a capillary action. So it is also saturated by capillary actions. Okay, so as I said before, if it's capillary actions, then we are expecting to have a negative pore water pressure at this point. So here water pressure 0, here is negative values. Okay, and as it goes deeper, it's a positive pore water pressure. And then from 5.4 until 20.6, we have a soft blue clay with water content is 28%. Okay, so in this assignment, I would like to see the plot of total stress, pore water pressure, and effective stress at all those depth. Okay, and I would like to see the plots on a real graph paper. Jangan pakai Excel. Boleh kelas?
Boleh.
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 Okay, so the assignments must be submitted by Friday next week. So the cut-off date is Friday next week, 5 p.m. So I will put in Putra Blast, the lecture today, the notes, and also this assignment. Boleh?
Boleh.
Alright. Any questions before we adjourn the class? We dismiss.
Doktor, yang recording ni Doktor save kat mana Doktor?
Nanti saya share dekat I give to your class rep.
Okay.
Okay, so I'll share the recording with your class rep and also share the notes in Putra Blast. Okay?
Okay.
Alright.
Okay, Doktor.
Alright, thank you so much everyone. Assalamualaikum. Bye.
Thank you, Doktor.
Thank you, Doktor.
Thank you, Doctor. Happy New Year.
Apa in Putra Blast
Doktor,
Doktor,
yes.
untuk soalan ni berapa tu?
What is it?
GS 2.7 kan?
GS untuk soalan ni.
Aha,
Tak ada bagi Ada bagi kat situ ke?
tak ada.
tak ada.
Yeah. Wait, let me check. Tertinggal lah tu. Yes, 2.7.
2.7 kan? Okay.
Thank you, Doctor.
Welcome.
Doktor,
Yes, yes.
about the site visit kan, do each of the member have
Ah.
to be like mesti ada dekat satu tempat ke we can go separately? Maksudnya satu orang tu dia dekat Kelantan, satu orang dekat Perak ke macam mana?
Oh, because of the pandemic and you are not in the campus, so I expecting for each of you ada your own site lah. It might be that you have to ask permissions and or it might be just like you ambil gambar je dan tengok then you macam tu lah.
Oh, but we can
And
do
if you
together
need
juga
any
kan?
letter from me,
Okay.
boleh. I just need one site. Yes.
Oh, so yang tempat lain-lain tu just like macam kita nak explore which one is like yang kita nak lah, yang the most lah.
Yes. The most that
Okay.
maybe the most information that macam tu lah yang worth
Ah.
to be presented lah.
Okay. Thank you.
Okay. I'll putting the slide in your Putra Blast now. You nak buat assignments. So it is under week 10.